So this video is going to work a little differently than videos in the past because I've got a worksheet for you. You can download that with the link or from the course website. What this is the Buckingham Pi Theorem, and I'm just going to talk you through it, and then we'll do a couple more videos that have examples. So here's the deal. The Buckingham Pi theory says that if an equation involving k variables is dimensionally homogeneous, then it can be reduced to a relationship among k minus r dimensionless products, where r is the minimum number of reference dimensions required to describe the variables. Okay, so now that I've explained that, go ahead and move on and watch the next video. Okay, I'm kidding. I actually want to diagram this sentence. This is very meaty. What the heck is it talking about? Let's unpack. So here's that sentence split apart for you. Let's think about what it means. If an equation involving k variables, so there's some equation that looks like u1, and it's a function of, say, some other variable u2, u3, so on and so forth, all the way to uk. K variables, that means 1 through k. Now I'm not saying they're all used, these are just placeholders. If it's dimensionally homogeneous, what does that mean? Well, it means that the dimensions of the left-hand side of the equation have to equal the dimensions of the right-hand side. Seems a little redundant because in physics equations that's always the case, or otherwise it's a bad equation. But if that's the case, then we can reduce it to a new relationship, and that new relationship is going to look like pi1 is equal to some new function. Instead of calling it f, we're going to call the function phi, and it's a function of pi2, pi3, and so on, all the way out to pi sub k minus r. So that kind of gets us the second line here. Among k minus r dimensionless products, that's the number of pi terms. And this pi has nothing to do with 3.14, by the way. It's just another variable that, for whatever reason, is the one we like to use. So what I'm saying here, we got k variables to start with. We're going to have a new relationship that is k minus r, so presumably that's fewer variables. So we're shrinking the number of variables to describe the same situation. How much are we shrinking by? Well, k minus r is the number of products, and r is the number of reference dimensions. What's a reference dimension? Well, these go all the way back to the fundamental base dimensions. So things like mass, length, and time tend to show up in fluids, right? Another set of base dimensions you could use, depending on your unit system, would be force, length, and time. And so there's a bigger set, right? There's 7 total reference dimensions, but these are the 3 that seem to be the most relevant, or the 2 different sets of 3. So k minus r, what that means is we start with k variables, we'll probably get to reduce it by up to 3 total. And so hopefully we're shrinking the complexity of the problem. So let me talk you through the steps on how to do this, and once I've done that, we'll give you a couple example videos that really unpack this. So the first thing you want to do is try and determine all the variables that are involved in the problem. This is by far the hardest step because it just takes some intuition and some understanding. But if you'd like a multiple choice checklist, here it is. We want all the geometry of the system, we want to capture the fluid properties, and we want to capture the external effects. And so you could start out, if you're really stuck, by writing the governing equations, things like the conservation of mass, conservation of momentum, so on and so forth. Once you've exhausted the list of variables that could matter, we want to express each of those variables here, step 2, in basic dimensions. So maybe we'll use mass, length, and time, or you could use force, length, and time. Why are these 2 different things? Well, force and mass are kind of related to each other using Newton's laws, and so we can either use mass, length, and time or force, length, and time, but it would be redundant to have mass, force, length, and time all in one. So an example of expressing that variable might be that the density is mass per volume, and so in terms of basic dimensions, that would be mass times length to the minus 3. Length cubed is volume, and it's on the bottom of this equation. So we would do that with all the variables from step 1. And then from there, that tells us the number of pi terms. This is the number of variables from step 1. The R is the number of base dimensions that you used in step 2. And so that's probably a number between 1 and 3 in this course anyhow. And so that gives us a number that is the total number of pi terms that we're going to need. And so now it's just time to build those pi terms. First thing we're going to do is pick a set of repeating variables. How many? Well, however many however many base dimensions we used. So probably 2 or 3. Okay, but there's a couple of caveats to this. First off, the idea is we basically want to pick a representative variable for each of our base dimensions. And so we need a variable that comes from the original list. It needs to combine with all the leftover variables in that list to form the pi terms. That's kind of what we're up to. And how's that going to work? Well, we want to make sure that of the variables we come up with, say that's 3 for r being 3, we want to include all the reference dimensions. So each variable is supposed to be dimensionally independent of all the others and appear in only one of the pi terms. And so the trick here is you don't want to use your dependent variable, the thing you're most interested in, as the repeating variable. And we want these things to be as close as possible to dimensionally pure. We'll use these guidelines in the next video to really unpack this. So just bear with me here. Okay, the next step is we're going to form the first of our pi terms by taking one of these non-repeating variables that we came up with and multiply it by a product of the repeating variables. So here are the repeating variables. Say we had 3 because we had 3 reference dimensions to start with. So these variables, they're going to show up in all of our pi terms. And then one by one, we're going to go through the leftover variables and stick them here. What are we going to do next? Well, pretty simple. We're actually going to solve for these 3 exponents, and that's going to make this whole thing unitless or dimensionless. And so we want to use the exponents here along with the dimensions of this one, solve for that to get it to be dimensionless. And then we repeat that for each of the non-repeating variables. And so what we end up with then is a pi group for each non-repeating variable. In other words, that's where we get this k minus r terms. After we've done that, the next step is just to check our work. That's fairly straightforward. Plug in the dimensions, make sure they actually come out dimensionless. And then what we want to do is, there's all kinds of reference tables for this. We have one in our text, table 7.1. And what we're doing is just finding out if we created something that looks familiar. So for example, maybe we created a thing that has all the same variables in it as the Reynolds number, but they're arranged differently. Well, you can, in step 8, just replace the thing you came up with the Reynolds number, so that gets us as close to as possible to customary terms. And the reason that's interesting is because it makes it easier to communicate with other engineers at other places. So then the last step is that we want to express the final form of these pi terms as this function here. So we've got the thing that we're most interested in, so this is the pi group that holds our dependent variable, and there's some unknown function phi of all of these things. And the reason that we've done all of this is that now we can go out and we can conduct the simplest experiment possible. And that's the experiment that only varies these independent variables to measure their effect on the dependent variables. And then what we can do with that data is we can make the graph, we could perform a regression, and eventually come up with that relationship. So this is really weird to listen to in terms of bullet points, especially step 4. Go to the next video, check out the examples. I promise this will come clear for you.